Centrifugal pumps increase the pressure of a liquid stream by adding kinetic energy to the flow. This kinetic energy is then converted into pressure inside the pump casing. The main components of a pump system are 1. The pump itself. 2. The pump driver, which is usually an electric motor. Other power sources, such as hydraulic motors or internal combustion engines, are sometimes used to drive the pump. 3. The coupling that links the power source to the pump. Now let's look at a bird's eye view of how the fluid flows through the pump, as well as a fly-through view to see the pump's interior from the perspective of the fluid flowing within it. In a typical radial flow centrifugal pump, the liquid is sucked into the pump from the intake pipe. The liquid then enters the pump through its intake and travels to the impeller eye, which is the region at the center of the rotating impeller. The liquid enters that region traveling in a direction that is parallel to the impeller's axis. Due to the impeller's rotation, the liquid is forced to rotate as well. As the liquid rotates, the centrifugal force causes the liquid to also travel outwards in a radial direction. This forces the liquid to the outer periphery of the pump's casing, which is called the volute. The volute is a region that expands the cross-sectional flow area as it wraps around the pump casing, gradually causing a reduction in fluid velocity and an increase in pressure. The liquid then exits the pump and travels down the outlet pipe. Centrifugal pumps have different configurations. The selection of a specific configuration depends on the flow conditions. A rough estimate of the type of pump that would be best suited for a given application can be obtained from a dimensionless parameter called the universal pump specific speed. The universal specific speed is given as the pump speed in RPMs times pi times the square root of the flow rate in meters cubed per second divided by 30 times the product of the gravitational acceleration in meters per second squared and the pumping head in meters raised to the power 3/4. As you can see, when we substitute the units for each term of the universal pump specific speed equation, they cancel out and we are left with radians. Hence the universal specific speed is a dimensionless parameter that does not depend on the unit system we use. English units can be used to obtain the same value of the universal specific speed parameter given the same flow conditions. Positive displacement pumps are suited for flow situations involving very low values of the flow rate and high values of the pumping head. In general, for values of the universal specific speed that are less than 0.1, positive displacement pumps such as piston, gear and screw pumps should be used. For universal specific speeds that are larger than 0.1, centrifugal pumps are used. Depending on the orientation of the exiting flow with respect to the incoming flow, centrifugal pumps can be classified into three main categories: radial flow pumps, mixed flow pumps, and axial flow pumps. In radial flow pumps, the flow comes in along the axis of the pump's shaft and leaves in the radial direction. In other words, the angle between the intake flow and the outlet flow is 90 degrees. Radial flow pumps should be used when the universal specific speed is between 0.1 and 0.8. This implies moderate flow rates and pumping head. In mixed flow pumps, the angle between the incoming flow and the outgoing flow is between 0 and 90 degrees. The impeller's hub has a conical shape to change the angle of the flow to the required one. Mixed flow pumps should be used when the universal specific speed is between 0.8 and 4. This implies high flow rates and a low pumping head. In axial flow pumps, the vector direction of the exiting flow is in the same direction as the incoming flow. In other words, the angle between the incoming and outgoing flows is 0. The impeller looks like the propeller of a ship and fits tightly within its pipe. Axial flow pumps should be used when the universal specific speed is larger than 4. This implies very high flow rates and a low pumping head. Depending on how and where the pump is installed, centrifugal pumps can be categorized according to the direction of the shaft onto which the pump's impeller is mounted, into horizontal pumps and vertical pumps. In horizontal pumps, the pump shaft is horizontal. Most horizontal pumps are mounted on rigid metal or concrete bases. The other type is vertical pumps, where the shaft of the pump is vertical. Vertical pumps are usually supported by the pipe on which they are mounted, or they can simply rest on the bottom of the tank from which they are drawing the liquid. Vertical centrifugal pumps can be further categorized into two categories. Dry pit pumps have their pump casing surrounded by air. This offers better access to the pump for maintenance and inspection, and protects the pump from corrosion and contaminants. Wet pit pumps have their pump casing submerged in the supply tank, or reservoir of the liquid that is being pumped. In this case, the driving motor is placed above the pump. Wet pit installation offers better cooling for the pump, and minimizes the net positive suction head since the liquid does not need to travel up against gravity to reach the pump. This decreases the liquid's tendency to cavitate. The significance of the net positive suction head parameter is discussed in the centrifugal pump operation section. Pump suction nozzles can be classified according to their location, into end suction, side suction, bottom suction, and top suction nozzles. End suction nozzles are the most common nozzle location for centrifugal pumps. In the end suction configuration, the liquid flows directly into the impeller eye. In other words, the flow does not need to make a sharp turn inside the casing of the pump to enter into the impeller eye, at the correct angle. Some pumps use double end suction nozzles, where the fluid comes into the pump from both ends. In the side suction nozzle configuration, the flow comes in horizontally from one side of the pump. In bottom suction pump casing configurations, the flow enters the pump's casing vertically from the bottom. In the top suction configuration, the flow comes into the pump casing vertically from the top. Pump discharge nozzles can also be classified according to their location into 1. Top vertical, 2. Top horizontal, 3. Bottom vertical, and 4. Bottom horizontal. A single-stage pump is simply one pump with a single impeller. A multi-stage pump is comprised of multiple single pump stages that are connected in series. The outlet of one pump becomes the inlet to the next pump within the multi-stage pump arrangement. All the pump stages in a multi-stage pump share the same casing.